Hello, my name is Radimus. I'm going to be going over negative binomial distributions and their properties. So for us who are in Stat A307, this is section 3.6, and these are my notes that I have on the section, and I'm just going to be giving a quick rundown as long as a Desmos calculator, which will allow us to be able to do really quick calculations for these types of problems. So, when we're doing problems about negative binomial distributions, there's only really three things that we care about. And number one is the independent and identical Bernoulli trials with the success rate p. So just a variable p, which means that every time we run a trial, there is a success rate, which is the rate at which p is a success. P can either be a success or a failure, as we can see here in this like string of trials. So here there's 7 trials ran. First one was a success, second was a success, third was a failure, and we keep going on. There are 7 total, and there are 3 successes here in this string. So if we were going to take a guess at what the success rate is, this isn't the success rate, but I would say something like 3 out of 7 because we have 7 total. Usually in our problems we're going to have a success rate given to us that we're not going to have to calculate, so this is just a variable that is being input to this function. Next that we have is trials observed for our successes. So this is going to be how many successes we are trying to get. R in this example is 3, because as you can see we kind of stopped here after the third success. So that brings up a nice property of these types of distributions, and that is that they're always going to have the last thing is going to be a success. So that's one thing that will help us be able to calculate other stuff regarding them. Number 3 is the x variable, and that is how many trials it takes to obtain our successes. For this, obviously that is 7. We tried 7 times to get that third success in our all of our attempts. So this is our example where R equals 3 and S are successes and F are fails. So our goal with all of these things is to find the probability of X. And X can be whatever. So it's another input that we have here. So let me state this as a problem. It would be something like this. If I have a success rate P and I wanted to figure out what would be the probability of having 3 successes within 7 tries. So that's one way kind of how we would state a problem like this. And I know it's a little bit clunky, but usually our variables are very explicitly stated and the problems are pretty simple to solve. So here are other examples that give, these are straight from the book. If we had a string of S, F, 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 S, S, this one has, again, all of these have R3, but this would be an example of where x equals 7 because we took 7 tries to get that third success. Over here, we again have the same exact thing. And the only point of having these two strings right here next to each other to compare them is just to show that there's different possible outcomes and they can give us the same x variable. So it could take the same amount of tries to get the same amount of successes, and that can happen in different ways. So over here, it's possible that we could just get them all at once, success, 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 and there's only really one way that can happen if x equals 3. So if I were to say x equals 3 and r equals 3, I know that I just had 3 successes in a row. Over here, we have x equals 4, which is just success, success, failure, success. So yeah, these are just all different examples for the same thing. And here's that note that I mentioned earlier. We always end with a success. And other previous trials contain 2 successes and x minus 3 failures. What does that mean? So if we look over here and just focus on that first variable at the end of the string, we know it's going to be a success. Therefore, for everything else, there's going to be x minus 3 failures. So let's take this over here. Not always x minus 3. This is actually x minus r. But so for this example, r equals 3, so x minus 3 failures. We have 1, 2, 3, 4 failures. 7 minus 3 is obviously 4. So look at that. I already know how many failures there's going to be based off of having x and r. Same over here. There's going to be 4 failures. Over here, 3 minus 3 is 0, so that means there's 0 failures. Over here, 4 minus 3 is 1, so that's 1 failure. So just more properties so that we can always know how many failures we had just based off of how big x is and how big r is. So we can get the same x from different experiment outcomes. I've already mentioned that. Right over here is just highlighting those two from earlier, that they both had an x equals 7. So how many different experiments yield the same x? So is there a way to calculate exactly how many different ways we can arrange these s and f's to get the same x? So this is the actual calculation for how that works out. Given that x minus 1 is our set of objects, everything before the last thing, because we already know this is a success, so we're only worried about x minus 1 elements, these 6 over here. R minus 1 successes equals 2 total. So we know that there's going to be 2 total successes. All that we have to do is take r minus 1, because we already have accounted for that last third one, right? So r minus 1 is 2. I know there's going to be 2 successes over here out of these 6 different things. So we do 6 choose 2, which if you don't know is 6 factorial divided by 2 factorial times 6 minus 2 factorial, 4 factorial. And we get 30 divided by 2, which is 15 different ways for us to get x equals 7. So that is pretty much the overall gist of the negative binomial distribution. And the types of problem that we're going to be solving is just using this formula most of the time. So we have the probability that x is what we want it to be. X minus 1 choose r minus 1 times 1 minus p to the power of x minus r times p to the power of r. So there is a derivation for this, and it's pretty simple, but we don't really care for that. The professor gave a very, very good explanation on it, and he even, instead of doing p to the power of x minus r, he just does 1 minus p to the power of x, and then he puts another p in front or something like that. Another thing to note is that r is always an integer, and that's just something obvious. So here's an example that we're given in the book. This is the problem here. We say p equals 0.1 and r equals 3. We're trying to figure out if x equals 20, what is the probability here? So I'm going to put this side by side over here so we can see this is the function that we're plugging everything into. I'll get to these later, but all that we would do is we would plug in 0.1 for p, r equals 3, because they gave us r equals 3, and x equals 20. As you can see, the probability of this occurring is going to be about 3% right there. So what are the odds that we're going to find a third defect if the odds of a defect occurring are 10%? So that's just this problem right here. We don't really care about word problems. We're just wondering about our givens and all of that. So another thing that this problem asks for is the expected value and the variance. These are the equation for the expected value, r divided by p, which in this one comes out to be 30. And there's the variance, r times 1 minus p divided by p squared, and that comes out to be 270, which we can also see over here calculated out perfectly. So, if you get any problem, they give you your p, your r, and your x, then you just plug those three values in here, and this should calculate out the probability. Right over here, this is going to be a maximum of 1. And then we'll also have this section right here, which is our expected value. This right here is our variance. So expected value and variance come out over here. Obviously, like, you're going to have to calculate those values out by hand, and this is just a really good checker just to make sure that whatever calculations you did were on point. So yeah, over here there's just a quick note explaining what all the variables are again. I already went over all of that. This right here is the moment generating function. I haven't seen any work with that either in class or in the book quite yet. The only real purpose of this moment generating function is to find the expected value. As far as I understand, you kind of have to take the derivative of this, and it's a very nasty calculation, but all of that just to get r over p. So just use r over p. Don't worry too much about the moment generating function. It's kind of a waste of time, unless it turns out that we're supposed to be using this. We're supposed to kind of know the derivation of it, how to get this. So if you guys need, I can make a video on the derivation of this moment generating function and even the how to take the derivative of it to get r over p. So yeah, one quick thing to note is that a lot of problems are not going to state p explicitly. They're going to call it a success rate. So a success can be defined as what we're looking for in the function and the odds that that thing happens. So that can be a little bit confusing. They're going to try to trip us up like that, I'm pretty sure, on our exam questions. So one thing to note is there's only two possibilities. It's either going to be the number that they give us or 1 minus that number. So for example, if like over here in this problem they explained it. They said that p equals 0.1 because in the problem they state that the process has a 90% effective, a 90% rate of success. So we're trying to find the rate of failures. So technically, the rate of success for our equation is 0.1, 1 minus 0.9. So all you got to do is you got to look, okay, what am I trying to find? And you see, oh, I'm trying to find the failure rate of this thing that is 90% effective. So then you just take 1 minus 0.9 in that instance. I don't like calling it a success rate. I don't know why the book does it or why the professor does it. It's a lot simpler to just call it either a frame of reference or a variable of interest. Like, hey, I'm interested in the failure, so then the failure is just going to be the opposite of our success. Either way, I hope that all of that makes sense. If you guys have any questions, just make sure to message me on the Discord. I am going to be posting the link to this calculator in our Discord as well, so that you guys can just plug in values and use this to check your answers for negative binomial distributions. I'm also going to be posting this page of notes in the Discord. Everything over here are the professor's notes from the actual lectures, so hopefully these can also help you out too. They're very confusing if you don't know already what binomial distribution is, negative binomial distribution, then this isn't going to make any sense. This is just a bunch of gibberish. So my recommendation is going and learning all of this first, Once you have a very good grip on what these variables mean and how to use how to do this calculation, then take a look at his lecture and all of this stuff, because then it'll make perfect sense. Then this is all very simple. And yeah, so he also has for the homework problems 48, 50, and 52. If you guys would like, I can also post solutions to those three. So yeah. Either way, so I'm going to end the video right here. Let me know what you guys think about these videos, if I should keep making them for our class, and whether they were helpful or not. So yeah, just either leave a comment or tell me in the Discord. Give me a DM. Alright, take care guys. Hopefully I can hear you from you guys soon.